test where the material is tested from 25%. Now I've heard ones in the SN curve, in the stress cycle curve, there's something like a damage curve.
Yeah.
And if the material is once put under a stress that is higher than this damage curve, we'll never have fatigue limit again. Well, I was wondering if that proof test is kind of dangerous towards that.
It depends. I mean, if in a pipeline, it could be harmful. Actually, it can be helpful too. You mentioned the SN curve, and the SN curve, comes down like this, and for steel has a limit at about 50% of the uniaxial tensile strength. Now, what happens is if, let's say I've got a pipeline or something, and I stress it to 125% of its operating stress. Okay. Now, actually, it depends on what its operating stress is. If its operating stress is well, actually, they do this sometimes. If the operating stress is 80% of yield, and you stress it to 125% of that, you're going to stress it to yield. But the way you make the pipe anyway is you take a piece of plate and you turn it into a U shape, and then you turn it into an O shape, and then you weld it to make the pipe, right, the long pipe, so it's got the weld going down the center here. And then you actually expand it, you put it inside a great big shell die, and you pressurize it to expand it to make it nice and round. Because after you've done this and this, it's not perfectly round. And so you want it to get exactly the same size, because you don't want two pipes where one of them's this big and one of them's that big and they don't quite match. Or one of them's, or they're both elliptical, and then you have to try to rotate them to get them to match up. So you actually expand it and yield the pipe into a little die. But then in the field, you weld the whole thing together, and then you pressurize it. If there's a little crack, and now we're going to just draw a picture of the crack, and you load this thing to its yield stress, you're going to plastically deform. You're going to get a plastic zone at the tip of that crack, okay, because of the stress concentration. This is going to be above yield. Even though the average stress of the whole part is a yield, the tip of that crack is going to be above yield. Now, if that ends up producing residual tensile stresses after you've done all that, then you might effectively see on an SN curve that you don't really have a fatigue limit, which is your question, okay? Now, on a DADN curve, all you've done is you're at a bigger delta K. You've shifted over on delta K, okay? On the so if I plot a DADN, if I got a delta K here and a DADN, and I'm coming up like this, okay, this is stage 2, stage 3, and stage 1. Essentially, all you've done is kind of brought that one over there. Effectively, you've got a bigger delta K than you think because of the residual stresses in there. Now, it turns out, depending on how the structure is loaded, in a pipeline, this might be harmful, but sometimes you end up with residual compressive stresses on this thing, in which case the thing goes like this, or the thing goes like this, okay? And in fact, this is all generally called the small crack phenomena. Okay, and then basically it says that as you get down here to very slow crack growth rates, really you get a lot more scatter. Okay, things get to be very well behaved in here, and then they're just tearing up in here, right? So it turns out there's a fair amount of uncertainty when you have very small cracks, and things like it doesn't even have to be a crack. It just in certain materials you can just have an occlusion, and there's a stress field around the occlusion, which can be either tensile or residual. Or tensile or compressive, residual stresses, and that just adds scatter down here. Okay?
Just want to introduce, we have someone here who's checking out the outside program.
Okay, go ahead. Tell us some more. You were working in Indiana, you worked in Michigan, that's about all I learned there.
From Indiana, I went to the University of Michigan, did mechanical engineering undergrad, and working for Intel out in Boston, Massachusetts for the last 4 years.
Oh, okay, you're the old digital facility.
Exactly.
Okay, make semiconductors. Well, we're not making semiconductors today. We're talking about chips and things like that. Another part of the course, we talk about semiconductors.
Thanks,
Okay.
Brad.
Welcome. Other questions? Did that answer your question? Okay. Things get really messy when you get to small cracks, and you're really talking about residual stresses around, very localized residual stresses around things. But the fatigue literature goes through whether you're helping yourself or hurting yourself. And I haven't talked in the fatigue literature. The fatigue literature for the old SN curves, you basically just did one stress, and your stress pattern was nice and uniform like this, okay? Constant amplitude. Another area of current research is looking at variable amplitude loading, where you've got some sort of, random noise of amplitude, which is like the real world, much closer to the real world. And every now and then, a great big thing like that can introduce some favorable compressive residual stresses, and they talk about crack retardation because of the big overstress. So when you said it made things worse and you don't get the fatigue limit, in my mind I started thinking, well, in crack retardation, a big overstress is sometimes beneficial because it ends up giving you a plastic zone which when you unload it ends up being compressive. So yeah, there's no simple answer when you get to those things. Okay, we were talking about X-rays, and a little bit later, I want to get through some of the other things. I'll actually show you some X-rays. It's going to be easier, I think, because I got to change the projector around. But let's talk a little bit about. We started talking about ultrasonics, and actually, one of the reasons I had this out. This is just a non-destructive handbook from the Welding Society. And down here at the bottom, they start listing different types of inspection. Let me close that down. You have visual examination, which every weld should be visually examined by the welder if no one else. But often you have an inspector that comes by who's an independent person, and he'll look at things. We've talked about radiographic. We're now going to talk about ultrasonic. We'll talk about magnetic particle today. Other types are penetrant examination, which we'll talk about, eddy current. Acoustic emission, we just mentioned briefly. It's not used very often because in general, you can't separate the noise, the random fluctuations from the real signals. Leak examination is basically, well, you've probably done leak examinations. I mean, if a plumber goes in and plumb something up, like they just put this gas line in across here, they're going to go in there with some soap solution, and they'll pressurize it with air, and they'll see if it blows bubbles at the joints, right? There are fancier leak examinations where you use helium gas and a mass spectrometer, and ferrite content examination has to do with looking at the residual ferrite in stainless steel welds, basically. So those are some of the different types. We talked about ultrasonics and how you can have different types of waves. In fact, the only two types of waves I showed you yesterday at the end of class were kind of these two, the transverse and the longitudinal, where you can have waves going through longitudinally, or you can have them give a shape change like this. There are also things called Lamb waves and surface waves. It turns out waves in solids get to be just as complex as the stress tensor. And so, in fact, if you, anybody ever study kind of earthquakes and how they look at the seismographs and things, they have waves that travel across the surface of the earth. They have waves that go through the center, and then some of them are transverse and some are longitudinal. So on a seismograph, they can actually tell about how far away something is by measuring the time lag between the transverse wave and the longitudinal wave. They have different velocities. And so the further away it is, it's kind of like looking at the redshift for galaxies okay, you can tell how far away they are depending on the red shift. Well, the shift between the transverse and longitudinal waves gives you some idea of how far away the epicenter of the earthquake was. Well, ultrasonic testing is just a little earthquake in the piece of metal, okay, as far as that goes. And we talked, I've showed you this type of thing before, where you basically have a little transducer here that piezoelectric transducer that generates something on the order, well, typical frequency turns out to be 2.25 megahertz, and we'll go through what that means in a second. But you generate waves in the material and they reflect off the edge. Now, here obviously, well, this one actually is an angle beam, and so you're shooting the beam this way. You can shoot it this way, and obviously you'd have a different time lag. If you just shot it out randomly in all directions on a curved surface like this, you get the signal you wouldn't know what it meant. In fact, that's one of the biggest problems in ultrasonics, is working with standards, standard shapes, standard geometries, so that you figure out what it is you're actually measuring. If you have a crack in here, you'll actually, rather than going straight through to the end and getting this peak, you'll get peaks in the middle from the reflections off those things. Now, what does it mean to be 2.25 megahertz? And Ryan's going to show you tomorrow in the lab an ultrasonic test unit. And that ultrasonic test unit probably has frequencies that you can dial in from about 1 to 10 megahertz. But the typical value is 2.5 megahertz. If the speed of sound in the material is 5,000 meters per second, and you've got 2.25 megahertz, which is we'll just round it off to 2.5 times 10 to the minus 6 seconds, then you end up with 2 times 10 to the minus 3 meters as the wavelength. Okay? That's 2 millimeters. That's the smallest thing that you can measure with 2.25 millihertz, roughly 2.25 megahertz. Okay? Now, 2 millimeters is two-thirds of 3 millimeters, and 3 millimeters is the 1/8 of an inch. But I said most of the codes will say I'm looking for flaws that are on the order of no smaller than an 1/8 of an inch. Usually we can ignore things that are an 1/8 of an inch or smaller. So that's one of the reasons they choose 2.25 megahertz. If you use 10 megahertz, you'd be down here to 0.5 millimeter, which is 20 thousandths of an inch. You can't find flaws that are 10 thousandths of an inch by ultrasonics. And in fact, you can find flaws by ultrasonics that are very close to the surface, because if this is my transducer, and actually the transducer might look this big, but it may have a actual transducer width of the source, because usually this thing's just encased in plastic, it's a piezoelectric element. But if this is the actual piezoelectric element that has a width delta, it turns out for a distance of 4 delta from this, we basically call it the near field region, and everything else is far field. In the near field region, basically the waves from this corner of the transducer and that corner of the transducer are defocusing the signal, if you will. Okay? You're just getting a mishmash. There is information there, and there are people who try to figure out how to do something with signals from the near field, but basically you can only measure from the far field. So if your transducer is a 0.5 millimeter, again, you're only going to be able, you can't even measure within the first 2 millimeters of the surface. So generally ultrasonics is for thicker plate rather than thin plate. Ultrasonics is fantastic and can measure things. If you're just trying to measure the thickness of something, I mean, they have little $500 or $1,000 ultrasonic gauges, so that if you got pipes, like they just ran the pipe over there for the gas, and it's been in service for 30 years, and you want to know how thick the pipe is, or you got a boiler and you want to know how thick the boiler wall is after all the corrosion, you can go in there and you can measure the wall thickness within 1/1000th of an inch. Because all you're doing there is just measuring the time delay from front to back. Okay? That's very accurate. You're not trying to use the wavelength, you're just using the time delay signal. But if you're trying to measure a flaw, then you can't really pick up something smaller than the wavelength in the material. So now, people do go, in fact, I don't know, do you have an ultrasonic microscope out in Hudson? Don't know.
Probably do.
Probably do, but they're about $500,000 experts. But they go to 100 megahertz, and you basically immerse your whole sample in a liquid, and then you hit it with 100 megahertz signals, and the 100 megahertz sound waves have lots of problems with attenuation and everything, but you then, basically it's triangulation like CAT scans. The computer, this is why it costs $500,000, the computer takes all these sound waves coming back and reconstructs them into an ultrasonic image, and just like the ultrasound that, when they're looking for a baby in the mother's womb, right? But the ultrasonic microscope, they go to 100 megahertz. And 100 megahertz, you can go into, look at that, you're now getting down to 100th of a millimeter, or something on that order. So 100th of a millimeter is a fraction of a thou, right? It's about half a thou, 4/10 of a thousandth of an inch. So you can actually see things at fairly fine scale. Ultrasonics, I think I mentioned last time, is basically starting to replace X-rays just because of the hazards and the extra cost of X-rays when you're taking the X-rays. This actually is kind of a description to a wave physicist, someone who worries about wave signals and stuff, of the near field, okay? If this is actually, if the wavelength is much greater than the source, then this is actually, this is the near field type of stuff. And you're basically getting, well, let's go down here. This is when you're trying to send out a nice sharp beam in one direction. And then when you're equal to lambda, you've got this. And then when you've got your source spreading out, you get the near field region, and you run into problems. I may have that backwards, but in any case, you get different types of signals that are harder to interpret. Now, in the liquid penetrant inspection, are you actually going to give a demo? Actually, you probably don't have time to do a demo of this tomorrow. So, but we can show you the type of cans and stuff. It's just little aerosol cans. And you come along and you clean the surface of the material with a solvent. Now, you have to be careful about some of the solvents. If you use a chlorinated solvent and you look for cracks and then you go weld over the area afterwards, which you often might do, then if you're welding steel, chlorine plus carbon plus oxygen in the steel gives you this compound, which carbon oxygen chloride, dichloride, which has another name. Anybody know what the name of this is? It's a gas. No, it's not cyanide. Cyanide is CN. This is actually maybe even worse. It's phosgene. And phosgene was one of the gases they used in World War I to gas the soldiers, right? So you don't like to clean steel before welding with chlorinated solvents, because when you weld later, you're going to expose the welder to phosgene. In any case, they typically use non-chlorinated solvents. In fact, in the nuclear industry, they require that the non-destructive test solvents be sulfur and chlorine free. Anyway, you clean the surface and then you spray this, typically a red dye on there, and the red dye will soak into the crack, and then they show you wiping off, and you can wipe it off with a cloth, or you can just flush it with the solvent again with this from the spray can. It will leave some of the red dye there, and then you spray on this white developer. Okay, the white developer wets the red stuff, and you end up with a little red mark. And so here's a standard reference radiographs, and this is an ASTM E433, and these are not. This is the standard. I've never thought it was a very good standard, but and then this is, well, there's two ways to do it. I talked about a red developer. You also can do it with a ultrasonic, not an ultrasonic, but ultraviolet liquid. Somewhere in here, I have a picture of Here's a picture of an operator at, this is a magnetic particle test rather than liquid penetrant, but they're basically the same thing. It's just one's on ferrous materials. And basically you put a current to, in this case he's looking for flaws in the pipe, and he's got a little bathtub underneath here, and he's spraying on this stuff. It looks sort of like a hot green material, like hot pink, the hot green. It's kind of a lime green. Looks like a lousy Gatorade or something. He squirts that on, and it has little magnetic particles, and the thing is magnetized, and up here he has an ultraviolet light behind him that he'll turn on, or actually it's probably already turned on. And he'll look at it, and so this is basically the some spots and a crack that's shining back in ultraviolet. This is also ultraviolet. Here's something that's got a bunch of surface cracks. This is probably from grinding and overheating the material and getting, it's like a dried riverbed on the surface. There's one. There's a good crack. Okay. They don't have a whole lot of the. Here's some cracks around a hole. Types of indications you get. There were one or two in here that showed the red dye. Most of these are magnetic particles. Here you go. Here's one with the red dye. You can actually see the sharper crack inside that, and the red dye kind of bleeding out around it. Blow that up a little bit. You'll see the crack inside. Now this one's not too hard to interpret, but one of the problems with magnetic particle testing, where you magnetize it, put a magnetic fluid in the steel, or dye penetrant, where you don't have to have a ferromagnetic material. One of the problems is interpreting things. I mean, if I went back to the very first one where I just have a bunch of white dots, are those deep flaws, or are they just surface pits, which are inconsequential? And so often you have people have to come in and interpret what these indications actually are. With the cracks in there, it's not too hard to interpret it, but with the a lot of other things, you run into problems. A lot of times you'll have corners, and you didn't clean the red dye off very well, and so you'll get a false indication at corners. And actually, the people who operate these things all the time, they make a little better than minimum wage, but they get pretty good at it. But a lot of times you need an engineer to come in and try to interpret the thing, assuming the engineer knows a little bit about testing. This is a dye penetrant test on some sort of casting, or looks like some sort of impeller or whatever, but the red dye leaking out of that. The magnetic particle test is essentially the same thing as the red dye test, only you magnetize the material. And here are the kind of magnetic flow lines around a simple magnet. If I have a notch in a magnet, magnetic flow lines go out, and therefore the iron filings, if you will be attracted to it. And the iron filings can either be ultraviolet sensitive, or they can be just simple colored iron particles. In fact, in the field, if you got some guy welding steel on a bridge with, you can actually do this in the field fairly readily. All you need is a power supply, and we have lots of welding power supplies out there in the field. And you put a fairly high current, and they have these magnetic prods, which actually is just a big conductor, and you basically run current across the weld. So the current's coming from this prod through here, and you might be running 100 amps. Now, it may only be at 5 volts, okay? But you run 100 amps through here, and you'll magnetize this thing, and if there's a flaw right there along the side of the weld, then you basically squirt. They have this little bulb, Brian could show it to you tomorrow, a little bulb full of very fine iron, magnetized iron powder, and you squirt it on there, and you can buy them red and green, different colors, and you'll see it line up. And that's how I mentioned when the Seawolf submarine, it wasn't an inspector that found the very fine cracks that were less than 1/8 of an inch. It was the guy who was grinding the weld smooth, and he he wasn't doing an inspection, putting iron filings on there, but you got this great big long submarine which develops some residual magnetism from the Earth's magnetic field, and he saw that the grinding particles were lining up. Well, he was basically doing a very sensitive magnetic particle test, and he was smart enough to know he didn't usually see that, and that didn't look right. He knew something about magnetic particle testing, and he went and got some engineers and said, there's something wrong here, and he was right. And it cost the Navy $500 million. Anyway, so that's sort of penetrant testing and magnetic particle. You can't do magnetic particle on aluminum or stainless, non-magnetic stainless steels, but you use dye penetrant on those. And they're not terribly sensitive, I guess is the kindest thing to, well, magnetic particle is very sensitive because it will actually, you get the concentration of the magnetic field. The dye penetrant is not terribly sensitive in many cases, or it's oversensitive. You get a lot of false indications, I guess is another way to say it, and you have a hard time interpreting it. But typically, if you're making fillet welds on some bridge or some building, and you want something other than visual, radiographic is just so expensive because you got to clear everybody out of the area to take the radiograph. Magnetic particle can be done. I mean, I've seen cases where they actually have the same guy doing the welding, doing the magnetic particle testing. That's not the proper way to do it. You usually have an independent person to do it. But it can easily be, relatively easily be done in the field, and you're looking for cracks in the steel. One thing before I get to eddy current, one of the things, one quality control technique, which is actually one of the most effective ones, is in the pipeline industry. In the pipeline industry, you're talking about something, if one of these great big gas pipelines or oil pipelines break, you can be talking about $1 million a day downtime. I mean, if you actually be talking more than that. If the Alaskan pipeline, when it was bringing 2 million barrels a day down, and it was, at that time, let's say $20 a barrel, not 50. But if it was today, it was 2 million barrels a day. That's $100 million a day of lost revenue while the pipeline's down. And it could easily be down for 2 months while someone's effecting a repair. So you could easily be into the billions of dollars. So it's a fairly critical structure, and so they will often do 100% radiography. Now that's a little bit easier because you're laying a mile of pipeline a day, and so you can have a radiography crew that's far enough behind the guys who are welding that you don't have to clear everybody out of the area. And so what they do is, the welders make pretty good money. In fact, there's a union in Tulsa, Oklahoma that controls pipeline welding everywhere in the world, because it was mostly American oil companies. It's the American Petroleum Institute specs, and this Tulsa, Oklahoma union basically has a monopoly on things. The Alaskan pipeline in the mid-70s, they could have done robotic welding and probably welded it twice as fast, but the Tulsa union told the oil companies, if you bring one of those robots on site, you'll never have a pipeline, okay? So it's basically extortion. And so they did manual welding of the pipeline. However, out there in the field, if they log the person who makes every weld. So they know exactly who made the weld. They radiograph it, and the next day you get the radiograph back. And if the radiograph flunks, the welder has to go repair it on their own nickel at their own time. And they're supposed to keep production going too. So, you know, after working an 8 or 10 hour day, if you screwed up and you got a defective weld, you got to go a couple miles back while everyone else is eating dinner, and you get to go repair your weld, and you don't get paid for it. Okay, you get paid for making good welds, not paid for bad welds. And that's just one of the agreements, you know, with the union. And in that case, the union's basically trying to say they want everybody to. They want good welders on the job. Another thing I always thought was interesting, if you're building a pipeline in Zanzibar or Iraq or wherever you're going to build it, the Tulsa Union requires that they fly in American food for these guys, because they found that if they're eating the native stuff, they're not as productive, you know. So you got to bring them the McDonald's hamburgers from wherever, whatever. But that's one of the parts of the contract. Okay, eddy current inspection is very specialized. It can be very effective. It can be very rapid. It can be very sensitive. And essentially, all you do on any piece of metal, it doesn't have to be ferromagnetic. It can be aluminum. It can be stainless steel. Is you just have a coil of wire that sets up a magnetic field, and that magnetic field induces a current, which we call eddy currents, in the actual workpiece. And that current basically you have another coil that picks up or senses the eddy current coil, and if there is a flaw or a defect, a discontinuity, the inspection coil, and usually these two coils are wrapped together, you can't see the difference, okay? You just see one coil, but there's actually 4 wires. One input coil with power going in to create the magnetic field, and another pickup coil, because this thing's traveling along and it's going to break the lines of the magnetic field. If the magnetic field is not nice and uniform, it's going to give you a blip on the eddy current. Now, the eddy current, and so I talked about pipeline inspections, and they put pigs down the pipeline, these instruments that might cost you $1,000 a mile every 5 or 10 years. And one of the things they do is eddy current. You got nice simple geometry and very sensitive. If there's a corrosion pit on the outside, they'll pick up every corrosion pit. And the size of the discontinuity, they'll say, well, this could be it. I remember once, about 20, 25 years ago, it's quite, it's probably 22 or 23 years ago now. One pipeline company had run a pig through some area in Louisiana. The pipeline company was in Texas, and they got an indication where it went under the river. Okay, the pipeline went under the river, and it wasn't a simple thing that they could just go out and get the backhoe and uncover the thing and go and inspect it. They had an indication, and so I had to go down there. A testing facility here asked me to go down there because they actually had a diving group, and they wanted to sell the opportunity to go and have a diver go down there under the river and look and inspect the pipeline. And I had to go down and tell the pipeline company what this indication could mean. And I came up with 10 different things that it could mean, about half a dozen of which were inconsequential. It was just a blip, okay? I mean, it's a signal, it's an indication, but you don't know if it's a crack, which is harmful. You don't know if it's a corrosion pit. And now, they have some experience with some of these things, and they sort of have some signatures, but it's just sort of a blip on the screen, and you've got to do something to try to interpret it. I don't know what they ever decided doing, but I remember they were happy as I just sat there and told them all the things that could be wrong with their pipeline. Of which about half of which were inconsequential.
How thick are the pipelines?
Typical pipeline is about 3/4 of an inch thick. It depends on the diameter, because the stress in the pipeline is just the radius divided by the thickness. Radius divided by the thickness times the pressure is the stress of the pipeline. But if you're running a gas pipeline if you got let's say a 48-inch diameter pipe, which is a common large gas pipeline size, it'd be 3/4 of an inch if you have 900 or 1,000 psi in there. If you just work out the stresses, it'll be about 3/4 of an inch thick. If you got a 30-inch pipeline, it may only be half an inch thick or less. Somewhere between. Very few of them are less than 3/8 unless you're getting down to 12-inch pipe, and I'm not sure if they pig 12-inch pipes. But they do other things. For example, I had an explosion a number of years ago. I didn't have the explosion. Edison, New Jersey had an explosion in one of their, I think it was 42-inch gas pipe. And this is at 800, 900 psi. They had flames 600 feet in the air. Okay, and just the radiant heat. There was an apartment complex across the way. And when they originally built this pipeline, the pipeline was in the countryside. And they actually have, the American Petroleum Institute has different safety factors. If you're going through an urban area, you have a much higher safety factor. You have to operate at a much lower stress than if you're just going to blow up some farmer's cow. We typically blow up half a dozen farmers' fields a year, but you never hear about it. Now, Edison, New Jersey, you heard about because they built up New Jersey. It's the most densely populated state, and there was a great big apartment building across the street. This particular area where the pipeline busted was an asphalt plant. you know, for repaving streets and stuff. And I didn't tell you the story, did I? Anyway, so they have on a big pipeline like that, there's enough money involved, you know, tens of millions of dollars a day if something like that goes down, just because of the value of the product going through it. They actually have a plane, a small plane will fly over the pipeline once a week. And they'll look to see if anyone's doing any construction in the area. You've seen things if you're hiking somewhere, or even in a residential neighborhood, you'll see a little warning sign, you know, underground pipeline, right? Don't dig here, you idiot. Okay, and they have something nationwide called Dig Safe. If you want to dig somewhere and you think there might be underground utilities of any type, water, electricity, gas, whatever, you just call up the Dig Safe number and they will come out, and they have to show up within 24 hours by law to tell you whether there's something in that area. They will mark it off and tell you this is where our pipe is, so you don't dig there. Well, anyway, this pipeline broke after about 30 years in the ground, and it was fatigue cracked, but it was fatigue cracked because the pipe had all kinds of heavy equipment marks on it. I mean, basically backhoe teeth gouging in the pipe. One of them, this was like 6/10 of an inch thick in this pipe, this 42-inch pipe, if I remember, it was about 6/10 of an inch, and the flaw was like 400 thousandths deep in the deepest spot. And a fatigue crack grew from that, and finally got big enough for fracture mechanics that the whole thing let go, and you had the 600-foot flame. Nobody got hurt, but afterwards they said, well, how come we never saw in the weekly flybys? Was the guy flying by not paying attention, which is a possibility? Well, it turns out they had a liquid pond that kind of moved around, and they had the heavy equipment backhoes, and if the guy was actually digging underneath the water, the guy, when he flies by, unless he was actually digging at that time, he'd never see any evidence of digging near the pipeline. These guys swore at the asphalt plant they had never dug anywhere near that pipeline, except there were multiple backhoe teeth for about 100 yards along this thing. Okay, so clearly they had. Of course, they also said that, and the plant had changed ownership several times, and if I remember, it was they claimed, these people had owned it since 1984, and they claimed that no one had done any deep digging in this area since they had purchased it in 1984. However, in the big hole that the gas pipeline blew out of the ground, they found an entirely buried 1988 Ford Explorer. Okay, Ford Bronco. So, sort of disproved that no one had been digging in the area. And if you know anything about asphalt plants and stuff, sometimes these guys are just mafia fronts. No, they didn't find it. It was a stolen vehicle. Okay. No, Jimmy wasn't in it, but it was sort of interesting. Anyway. Just to listen to these people try to explain the 1988 Bronco when they claimed they'd never been digging since 1984 in the area. Anyway, clearly there'd been illegal digging in the area, and it was damage to the pipe. Almost all the pipelines that fail is due to construction damage or damage to someone illegally digging in the area. Anyway, what was I going to? Oh, I was talking about eddy currents. So eddy currents are very specialized. You can use them in pipelines. They use them in pipe mills where they're welding like stainless steel tubing, and they're coming through there like 40 or 50 miles an hour, and they'll have a little eddy current sensor, and it can pick up things at those frequencies. Okay? And so you're welding this stuff, and you pick up the defect. If the weld's not perfect, if it's got lack of penetration, lack of fusion, or it's got a crack or something, you'll get blips on your eddy current. What else did I want to talk about? Talk about eddy currents. Let me see what else is in that book. If not, then I can go to my X-rays and give you some idea of some of the X-rays. Okay, we covered everything. So let's go to some X-rays. So there are these nice handy-dandy ASTM books. This is Reference Radiographs for Steel Fusion Welds, Volume 2, 1/4 inch to 3 inches, inclusive. Fortunately, I bought these a long time ago when they only cost about $200 or $300 a piece for the book. Nowadays, they're getting like $1,000, $1,500 a piece for these books. But this one over here is aluminum and magnesium castings. It's not welds, it's castings. But this one's labeled aluminum gas porosity elongated 3/4 inch thick aluminum. So, let's see. Open that up. Increase the intensity. And so you've got 8 standards here. Now, none of them says this is acceptable or unacceptable. This is just the cleanest and it goes up to the dirtiest. And if I'm purchasing a material, I can say, I want aluminum castings that have gas porosity no worse than number 2. So that's a standard that I can set. So these are, I'm probably not going to choose number 8. There are lots of times in the aircraft industry, they'll say it must be number 1 or better, or number 2 or better. Okay? And they just use this as an agreement between the purchaser and the seller. So in this particular one, the very front, they have them for aluminum castings and magnesium castings. They have them for 1/4 inch and 3/4 inch material. And the types of defects are gas holes, gas porosity, round or elongated, shrinkage, or foreign material. Oh, there was one I wanted to show you. Oh, it's over here. This is for aluminum welds, and this one. Oh, no, this is steel welds. Where's my aluminum welds? Here's, yeah, this is one I'll show you. This is aluminum welds, and this is a crater crack. There's a little crack right there. You can see that little line there. This is called undercut. A real X-ray viewer, you'd be able to change the intensity and you'd be able to brighten that up by bringing up more light if you wanted. These I wanted to show you because these are tungsten inclusions. Okay, tungsten being much heavier than aluminum, you typically weld aluminum with gas tungsten arc welding. And so this is one piece of the tungsten electrode. You actually see the cylinder of the electrode just remains in there. Okay, it's not too hard to pick up tungsten inclusions. You can train people to do that pretty well. Okay, as far as that goes. This is steel welds. This burn through, there's a void right there. There's weld metal here, there's weld metal here, but right here, the thing's got holes in it. You didn't have to need an X-ray to prove that. You can see it with your eye. But some of these this one is what they call icicle teardrops porosity. These are ungraded. These are just examples of the types of things that you're going to be able to pick up.
What's undercut?
Undercut is due to fluid flow in the weld pool. When you're going very fast, or if you're using the electrode at the wrong angle, when you're actually welding, the pool, this is the plate you're trying to weld, and this is the solidified weld metal down here. The arc up here will actually create a depression, and the metal flows behind. So if you've ever been in a motorboat, and you look behind yourself as the motorboat's going through the water, and you actually see the water has depressions and mountains in it because of the fluid flow coming behind. Well, if along the sides, now looking at the weld in cross section, if I end up, this is my plate, if I end up with little notches right there at the edge of the weld, actually the notches would be the weld metal. If I end up with little notches there from freezing in the undercut, we're going to call it undercut, it's just a little notch right on the surface. And in fact, I had a gasoline pipeline. There's a 28-inch diameter gasoline pipeline that goes from Texas to Chicago. It has gasoline in it. And about 6 or 7 years ago, they had a leak of this thing, and it flooded the farmer's field in Texas. And it turns out they had big heavy rains at the time, and they tried to dam off this little drainage ditch where they lost 12,000 barrels of gasoline. Big problem, they lost the pipeline going to Chicago. And so gas prices went way up in Chicago back in, I don't remember, it was 1999 or 2000 or whatever. because the pipeline was down and they had to truck it in or use other pipelines from other parts of the country. And that was one of the concerns with Katrina, because for a few days, there's a big gas pipeline that comes up to New Jersey, and that was down immediately after Katrina, but within a week they had it back up and running. But the question was whether we were going to have gas on the East Coast. Anyway, this thing had an undercut, and then they coat the whole thing in the old days used to be coal tar, but they put a corrosive protection coating on these things. And over time, the coating may come off, and in fact, it did come off, and there was corrosion here. So then the question became, was there undercut from the original manufacturer of the steel in the steel mill 27 years before? Or did this thing fail because it had a corrosion at the toe of the weld, which led to a fatigue crack? Everyone agreed it was a fatigue crack that caused it to grow, but then it was chicken or egg. Was it corrosion or was it undercut that got the crack started? And it turns out I was able to prove it was undercut by looking at other parts of the pipe and also by fracture mechanics, so far as that goes.
About how deep are some of these big pipelines buried in the ground?
Typically 10 or 12 feet. I mean, they got to be below the frost line, where the frost line is, except in Alaska, where you want to be above the ground, because you can't go below the frost line. The frost line in the permafrost is 1,000 feet. Okay, so I didn't pick out a figure one. This is slag inclusions in steel welds. I guess this one actually is a little bit harder to see, but that's what people are looking for. This is actually more typical of what an MD is going to be looking at. Okay, an MD is going to be looking at your lungs, and he's going to see little changes in gray, and he's going to say, you have cancer. You know, and you say, do I? You know, a lot of this stuff is more art than science in terms of interpreting these things, particularly when you get to the medical field. I did want to show you some cobalt-60 radiographs, since I maligned them so badly the other day. This is for steel castings 4.5 to 12 inches thick. And here's a crack. This is cobalt-60 radiation. And this one you can see, I mean, this is life size, guys. So here's your crack. But when you're getting to something that's, I don't know, it doesn't say on here exactly how thick this one is. The U.S. Navy, by the way, developed these, the David Taylor Research Center, and gave it to ASTM because they wanted people to be able to check their pressure vessels and things like that. But there's a crack there. You can see the crack, right? That one's not too bad. This is category D. If I showed you category A, or whatever, you'd find that you'd have a hard time really believing that there was a crack there. So, anyway, I guess that's, anybody have any questions? Tomorrow we'll go through the, in the lab and show you demonstrations of spot welding and arc welding and plasma cutting and things like that. Has anyone gotten the list from Jerry, the email list? Brian, can you get that and send everybody a note? Because someone wanted to get everybody together to do the homeworks, right?
What's this?
The email list from Jerry. And you gotta watch the other 25 videos, right? Have a good time. I'll see you tomorrow.